All right, let's go ahead and get started. I do want to welcome you all to Unit 11. This is Solutions. I want to especially welcome our new subscribers from, let's see, Vancouver, Washington. Vancouver, Washington, this is Lewis and Clark High School. So welcome on board, and hope these videos are helpful for you all. So let's get started. Here we go. Unit 11, Solutions. I want to start with a little bit in the way of introduction and some definitions. At the very beginning of the year, we were talking about the differences when we were talking about matter, we were talking about the differences between homogeneous mixtures and heterogeneous mixtures. What do we mean by a homogeneous mixture? Well, it's a mixture that's the same throughout, right? The same throughout, as opposed to a heterogeneous mixture, which is a mixture of things that are not the same throughout, right? Well, as it turns out, a homogeneous mixture and a solution is the same thing. So we'll start there. A homogeneous mixture and a solution are the same. Okay? Every solution is a uniform mixture of one or more solutes dissolved in a solvent. So let's kind of define solute and solvent. For example, when I mix, say, salt in water, I mix salt together with water, the solute is the salt crystal that I'm putting into the water. The water is the solvent, right? The water is the solvent. Now, I don't want you to get the idea that the solute is always a solid and the solvent is always a liquid. For example, let's just say that I put a little bit of, I want to mop the kitchen floor, and I put a little bit of Clorox. A little bit of Clorox into a big bucket of water. Well, the smaller amount, the Clorox, is the solute. It is dissolved in the solvent, which is the larger volume of water, right? So we now know what a solute is and a solvent, all right? Okay, let's take a look at a few other examples in this note right here. It says solutions aren't just solids dissolved in liquids. They could also be gases dissolved in liquids. Think about what happens when you pop open a nice, refreshing can of Coca-Cola. The CO2 gas comes out of the solution once the pressure is released. In other words, the CO2 gas was the solute dissolved in the solvent of the liquid Coca-Cola, right? All right, so that's it. So that's a few definitions. We've got a few more. It says there is some maximum amount of solute that can be dissolved in a solvent. There's some amount that you can dissolve of solute into solvent, and that's it. You can't put anything more in there. When this amount is reached, the solution is said to be saturated. So in other words, a saturated solution has as much solute dissolved as is possible. If you put salt into water, if you put a little tiny bit of salt in water, you stir it up, that's fine, no problem. It's going to dissolve in the water. If you put a little bit more, stir it up, a little bit more, it's still going to be dissolved. But at a certain point, you can't put any more salt in there without it falling to the bottom of the container, whether it be a glass or beaker or whatever it is, and therefore it is saturated. So at that point, where you've put the maximum amount of solute into the solvent, the solution is said to be saturated. Okay, it's saturated. Now, if there is less than the solvent can hold, less solute than the solvent can hold, we call that, it's not undersaturated, we call it unsaturated, okay? So unsaturated has less than the maximum that can be held. It's less than the maximum that can be held. Now, under some circumstances, a solvent can actually hold more than the amount it should be able to. We call this a supersaturated solution. So there are some special circumstances that we'll talk about a little bit later that are called supersaturated solutions, where it shouldn't theoretically be able, the solvent shouldn't be able to hold that much solute, but it does. We call those situations supersaturated solutions. So let's go over those definitions again. Solute, dissolved in the solvent. Saturated, you've got the maximum amount of solute that can be held in the solvent. If you have less than that, we call that unsaturated. If you have more, under these special circumstances that we'll talk about a little bit later, that's called supersaturated, okay? So supersaturated solution. All right, good. Now, I want to talk a little bit about how we define the concentration of a solution. I brought this up in a little bit of detail when we were talking about in our stoichiometry unit. This is unit 9, I believe. We were talking about a problem that involved a concentration unit called molarity. So I want to bring that up again. All right, I want to talk about what do we mean by molarity. Well, molarity of a solution is defined as the number of moles of solute per liter of solvent. And the symbol for that was the capital M, as you recall. Okay, so if you have, for example, a 0.005 molar solution, that means you've got 0.005 moles of solute per liter of solvent. Okay, all right. So that's kind of the definition of molarity. We're going to use that to solve a simple problem here. Let's take a look at number 1. Example 1 says this. If a solution contains 3.458 moles of copper 2 chloride in 1.500 liters of water, what's the solution's molarity? What's the molarity? Well, molarity is moles of solute per liter of solvent. Moles of solute per liter of solvent. Well, how many moles of solute do we have? We've got 3.458 moles of copper 2 chloride. That's the solute. What about liters of solvent? 1.500 liters. So we'll divide those, and when we do that on the calculator to the correct number of significant digits, by the way, which is 4, we're going to have 2.305 moles per liter, or we can write it as 2.305 molar, and that's our molarity. Okay? That's the molarity for that solution. That's the concentration for that solution. 2.305 moles of copper 2 chloride per liter of water. That's pretty straightforward, isn't it? All right, let's keep moving. Let's take a look at another example. It says a solution is made by dissolving 95.7 grams of sodium hydroxide. Now be careful, molarity is moles per liter, not grams per liter. We want to make a 1.00 liter solution. What is the concentration of the solution? All right, so here we go. We're going to have to convert that number of moles, the 95.7 grams, to moles. So 95.7 grams, we're going to do some dimensional analysis here, right? I need grams on bottom of sodium hydroxide because I've got grams on top. I need to cancel, and I'm left with moles of sodium hydroxide. So where do I get the 40.0? Where did I get that 40.0 from? I added up sodium and oxygen's, hydrogen's atomic mass from the periodic table, and I got 40.0 grams of sodium hydroxide, right? So when we do that, we get 2.39 moles of sodium hydroxide. We're told that it's just a 1 liter solution. That's pretty easy. Just divide by 1, and we get 2.39 molar sodium hydroxide. That's the concentration of our solution, and we're done with number 2. Okay? Those are pretty easy questions. They'll get harder a little bit later. Let's take a look at the next one. The effects of temperature on solubility. Okay? So remember we said that there's a certain amount of solute that can be dissolved in the solvent, right? And the question is, how does temperature affect that? Think about how you can dissolve more Nestle's chocolate powder into hot milk than cold milk, right? That's a fact. If you want to put more Nestle's, if you want to make your milk more chocolatey, you heat up the milk, okay? You heat up the milk. Also think about how you can make iced tea really sweet by boiling the water before adding the sugar. All right, so that implies that the hotter, or the warmer I should say, it doesn't have to be hot, but the warmer the solvent is, the more solute that can be dissolved in it. So in general, the solubility, or the amount of solute which can be dissolved in solvent, increases as the temperature increases for solids dissolved in liquids. For solids dissolved in liquids. Okay? Hope that makes sense. All right, let's take a look at this diagram here. The diagram at right shows us that for most substances, the higher the temperature, the greater the solubility. Okay? Calcium sulfate seems to be an exception to this rule. So let's take a look and try to understand this chart just a little bit better. Okay? We want to understand this just a bit better. I'm going to increase the size of it just a little bit if I can. There we go. And what I want you to see is this. What I want you to see is that as I move from left to right across the periodic table, just like that, across the page. The temperature is increasing. It's going from 0 to 100 degrees Celsius. What we see on the y-axis is the solubility of, in grams, of in 100 grams of water, right? In 100 grams of water. So notice that for almost all of these substances, as you move left to right, what's happening to the solubility? The solubility is increasing. So let's take potassium chloride, for example. Let's take this one right there. If I look, for example, at, let's say 40 degrees, right here. 40 degrees, and I go up, up, up. This is the solubility of potassium chloride. In other words, I can dissolve, let me go across now. It's not quite 40. It's a little bit lower than 40, but not that much lower. It's about maybe 39, 38, 39, right? About 39. That means that at 40 degrees, I can dissolve 39 grams of potassium chloride in 100 grams of water. But what happens if I'm not at 40 degrees? What happens if I go all the way up to, let's say 90 degrees? 90 degrees is right here on that KCl line. So if I go across, that's about 55 grams. So at that higher temperature, I can dissolve more of the potassium chloride, right? I can dissolve more of the potassium chloride than I can at the lower temperatures. Now, there are some exceptions. This one right here is an exception, all right? So that's an exception to the rule. So we'll keep that in mind. The general rule is that as temperature increases, solubility increases, but there are some exceptions to that rule, okay? So I hope that makes sense. Okay? All right, let me reduce this again, just like that, and we're going to move on. All right. Folks, to kind of elucidate that fact, what we're going to do is we're going to think about a Coca-Cola. Okay? Everybody loves Coca-Cola, right? Think about how a cola goes flat very fast if the can is left out on a hot sidewalk, but not so fast if the open can is placed in the fridge, right? If you open a can of Coca-Cola and you don't drink the whole thing, and you put it in the refrigerator, it's going to last longer. I mean, when I say it's going to last longer, you can drink it 10 years later if you want to, I suppose, but it's not going to have the bubbles in it. It's not going to have the gas in it, right? It's going to go flat a lot faster if you leave it outside on the hot sidewalk, right? So the point is this: as temperature increases, solubility increases. That's the rule. There are a few exceptions, okay? Now, for gases dissolved in liquids, the opposite is true. The warmer the solvent, the less gas that can be dissolved in the liquid. That's why we have this example of the Coca-Cola, because of the fact that for most substances, as you increase the temperature, solubility increases. But for gases dissolved in liquid, it's just the opposite. Again, the colder it is, the more soluble the solute is in the solvent. This time it's reversed. Let me just make sure we understand that point. And I'm going to end it with this point again. For most substances in which we have solids dissolved in liquids, as you increase the temperature, solubility increases. As you increase the temperature, solubility increases. But for colas, or not colas, for gases dissolved in liquids, the exact opposite is true. The warmer it is, the less soluble a gas is in a liquid. Not more soluble, less soluble. Folks, I think that this is a good place to end this one. And next time we're going to be continuing on our study of solutions and solubility. So I'll see you then. Thanks. Bye-bye.